Hi everyone. Today we're going to continue with our lectures and going to look into chapter 3, which is regarding a thermal control system. Now, as we have seen, the first chapter structure becomes very important. Then we went into power system. We just completed the power system. We know for the fact that the power system is going to consume electricity, and then the electricity is going to actually power our subsystems on board the satellite. Later, that will be also subjected to a heat generation on board. So don't forget, there is an internal heat generation that we need to manage, and external heat sources that come from space that we need to manage as well. So thermal control, it's mandatory basically for any satellite, and in fact it is very challenging in fact in some conditions whereby we need to really manage the even temperature regime for all those subsystems that we have. Let's move on. Now, let's look at the condition, the typical condition that you have always. Assume that you have a satellite basically flying, or Earth-oriented mission flying basically, or orbiting planet Earth. Typically, there will be two very visible conditions: the sun phase and the eclipse phase. So, as you can see, when satellite moves into eclipse phase, it gets very cold for satellite, and come back to that sun phase, it's going to have a heat, I would say, environment. So therefore, there's a cyclic effect, heat and cold, or rather hot and cold throughout the orbit. So if you look at the LEO satellites, low Earth orbit satellites, maybe at about 500 kilometers of altitude, you will have easily about 19, at least about 19 sort of orbits in a day. So 19 times you're going to get hot, and 19 times you're going to get cold. So there is basically I would say a temperature variation, quite a drastic one that we need to manage. So the fundamental will be, I expect all of you to know heat transfer. I think you might have probably been exposed to thermodynamics, heat transfer, aerothermodynamics. Therefore, I think the subject of heat transfer you need to practically revise in that sense. But I'm going to go through a quick revision for heat transfer. Then thermal environment, that we're going to define what is the thermal environment that we have in when satellite is flying and subjected to what kind of heat that we will actually see, and analysis and design. This is a very huge topic. We can actually keep on going. As I've said, like even the power system, we can end up doing in the whole semester. Likewise, thermal analysis, actually you can go out and do thermal analysis for satellites specifically for the whole semester. In fact, there's so many details actually we can work on. But again, what we are going to do is that we're going to cover within about 2 weeks, so that you can get a good snapshot of thermal control, how to do it, what kind of devices there, and how to basically calculate some basic parameters. Then there is also hardware involved. I'm going to expose to you very typical hardwares. In fact, I'm going to expose to you all those hardwares is available, which are available for space application, and I'm going to also indicate for you what kind of actually devices or hardware that we use for satellites and other spacecrafts. Thermal test is quite typical. When you want to qualify any hardware, you need to do thermal tests as well. But this we are not going to go into that thermal test of specific hardware development, but it's more into basically how to quantify it, how to basically do a parametric study on the actual heat loads that you have. Bear in mind, it is a very, very complex system. So the goals and possible thermal control for any mission has to be really, really looked into. It is, if you just ignore thermal control, it maybe will be leading to a catastrophic, I would say, cost or failure. In fact, system and technology, what is accessible, and again, when you talk about system and technology, we need to know what kind of hardware that we have, whether we can afford the hardware that is offered, and everything. The more complex and the more efficient the hardware is, it is going to cost you, well, a bit more money in that sense. Then realization of the concept itself. So there's very clear demarcation on what approach that you are going to do. So we will define that clearly. Okay, these are the options that we have. In fact, how to choose that, and then what are the options that we are going to actually proceed and start selecting all those pathways. The final one, thermal control of ISS, International Space Station. Now, why I'm including space station in this discussion, because when we have a mission, a manned mission, the thermal control system is going to get very, very, very complex. So therefore, if you look at it, let's say a satellite that we have, you don't have a human on board, then it's fine. It is relatively straightforward compared to if you have a human on board. Now, reason being human, well, all of us are basically heat spots. So when we walk around, well, we walk wherever we want, maybe in the cabin. So the heat loads are basically is going to change with respect to the time and with respect to our actual coordinate. So it becomes very complex in that sense, and we need to. I will actually show you what kind of thermal, or just an example of a thermal, a complete thermal control system for a space, for an international space station, which I say is quite complex in that sense. So just for a general discussion. Now, why we need thermal control? I think this is well defined. Existing temperature margins for spacecraft hardware. All our hardware that we have on board, they have a strict temperature regime that we need to maintain. Minimum and maximum temperature that we have. I will show you in a bit what kind of typical regimes that we are talking about. The problem that we have is that there is no one regime. There is a variation of regimes. That means not every or each and every subsystem is going to operate in one single regime. No, there is so many actually equipments that we have. They have their own regime of operation. Then you have also non-steady state external heat loads. This is a very, very typical problem that we have in space. Now, as we have seen just now, we have two phases, clear phases, the sun phase and the eclipse phase. So in the sun phase, there is an external heat load. So what is going to happen to you is that you are going to get heated up. The spacecraft is going to get heated up. The spacecraft is going to get hot. And how to actually control it? You remember the important item here is that to make sure, or rather to ensure all our equipments are operating at a specific given regime, temperature regime. So that is the challenge. You want to ensure that if you don't control it, you will be out of the regime and it is going to actually lead to a catastrophic failure. So that is clear. Then you have a thermal control. So assume just now I was talking about well, equipments. Now assume that actually the humans are in the actually space, I would say vehicle. So that means we are also more or less like an equipment, have our own actually temperature regime, maximum and minimum, that we need to also provide. That means the thermal control system should ensure that the human are comfortable to be in the cabin or to be in the spacecraft, and he can actually survive, or he or she. So that we will see what kind of constraints are there. Then you have a restricted heat rejection. Now, this is a very important element that all of you have to remember. Within the spacecraft, we know for the fact there are fundamentals of conduction, convection, and radiation. These are the three modes that actually a heat transfer can occur. Now, all these three can happen within the spacecraft, but from the spacecraft to the space, there is only one mode, radiation only. So, which means that if I want to eject any heat from the spacecraft itself, I have only one mode, radiation mode, and that makes the whole process, or rather whole job, even more challenging, because I have only one mode to rely on, and how there's only radiation is available. And remember, if I want to control my temperature on board satellite or even a spacecraft, I have only one mode, which is the radiation can come in. So I need to devise all those systems, all my thermal control techniques coming back to actually the radiation, I would say, endpoint. That is important. Okay, this is very important. Not like, let's say, cooling systems here. You can actually cool a building, for example, using convection basically. It's easy because it's your water and it's no problem. But then you can't actually do, it's very challenging if you want to just use only radiation. That's very crucial. Then as you can see, likewise we have two different phases, the sun phase and that eclipse phase. Therefore, when you go into eclipse phase, it doesn't mean actually you don't need any heat. You do need heat. If you don't control it, you may actually go beyond the minimum temperature. That means you can get very cold. You can get even up to about negative 30, negative 20, negative 30 degrees. So we can't afford that either. So on that mode, you need to heat up the particular spacecraft or rather a particular environment. So we need to introduce basically heating inside. It's just like in the winter, probably in overseas, in a European country, during the winter you need heating to keep basically the comfort level of the cabin or even the place that you are in. Okay, go on. So now, again, this is going to be a revision for you. I think all of us are quite clear. Heat conduction. There's first thing is the very basic heat conduction. That means you have a material, you have a device, and based on the device, from point A to point B, basically you can heat can get transferred through conduction. That means you must have a medium. But all of us are clear with that. Again, just to, for conduction, what is important is that the thermal conductivity of the particular material. So if you have steel, if you have aluminium, aluminium is quite popular or rather quite typical in spacecraft. So some parts, most of the aluminium parts are there. Basically, you should know that the material involved is basically aluminium, and it has its own conductivity, thermal conductivity. Then the distance. Well, if you have a beam, then you should know basically the distance for the beam, material, and therefore the temperature point A, temperature point B. Therefore, the whole heat conduction can be calculated. So coming back to heat convection, basically there should be, if it's the medium itself, it is not a metal, it's not solid, it is a fluid. Then we use a convection. All of us know that. Again, just like a thermal conductivity of material for conduction. Convection, what is important is that the film coefficient or heat transfer coefficient. They're very typical. You look at thermodynamics books, they will say that it is a heat transfer coefficient, H. This has to be found. So, all right, these are the basic. And from here, we can extend to heat transfer. So what is heat transfer? Simply, now, if I have not only one material, if I have a multiple material, technically the formula that we have used for a single material also can be actually extended to a multiple material just by actually redefining the thermal conductance with different kinds of materials, etc. So this can be actually easily done. And if you look at conductance here, it is not only specific basically for material, but you can use, you have 5 different materials. Let's say this particular A to B has a different aluminium than B to C, let's say a steel. So technically you should be able to use this formula to calculate the actual heat transfer. And this is the most important that I've mentioned to you. Now, if you look at it, radiation is based on Stefan Boltzmann's, I would say, law. So based on that, radiation is nothing but emittance. Emittance for gray body 0 to 1. You have a gray body 0 to 1. That is actually emittivity. Now, if it's a 0, then you should know that you are almost not emitting anything. So you are almost a heat absorbing body, a black body. Okay. So if you have a 1, so emittance is very, very high. Very, very good, or a white paint, for example, or a polished surface, that is quite typical. And Stefan Boltzmann's constant, I think all of you know this, and this the radiation actual relation have been established based on the Stefan Boltzmann's law, and A comes in. surface comes in. So more important is this, you in any heat transfer, the surface area is extremely important, and you need to know what kind of actually heat transfer, what kind of mode is going to happen. Convection, you have conductance, or radiation. These are the three modes that actually you have. You need to establish that, then use a particular formula. Then comes the heat transport. Now heat transport is very particular. When a fluid is transferring heat and it has a flow, that means the fluid is moving, circulating, then we can even actually calculate the heat transport by using this particular relation. We have seen this, mc theta basically. M dot is mass flow. It can be any fluid that usually we use. If you look at it, typically this kind of systems will run into fluids like water. That's simple. It can be just the water, can be ammonia, etc. So depending on that, so the faster the mass flow you have, the faster mass flow you have, the better heat transport that you will have. So depending on the application, how much you want to cool down or how much you want to heat the system, you need to provide the mass flow. So all this is very, very important. It's just a revision one. Right. Now, what exactly it is, you must understand there's an energy balance. No matter what we speak, okay, the actual heat, the net heat, basically, how you are going to calculate, it is nothing but the heat which comes from outside. Now imagine this is a satellite. Heat comes from outside, heating you up. Don't forget there are also heat from inside. You are operating on board computers, you have battery. Remember, battery is also emits heat. So you have internal, external heat, environment, and internal generated heat. And this is going to actually give you the total heat, and the total heat is the net heat that we are talking about. And this, if you want to find the temperature, with respect to maybe a certain volume means that there is a material defined in the volume, maybe it's steel or maybe it's aluminium. So you want to see the actual heat basically is involved in that particular structure, is nothing but mc delta t. That means that mc theta. So you should be able to find, this is, remember, you can actually do this in 1 dimension or you can do in 3 dimension. This is almost delta, but you can have a 3 dimension, that means x, y, and z. For numerical approaches, we can actually always calculate for the 3 dimension temperature variations. Okay. Now, again, it's just an again fundamental radiation. Remember the formula that actually I showed you. You have seen that before. Radiation is nothing but it's just that came from Stefan Boltzmann constant, and again the C is Stefan Boltzmann's constant. Stefan Boltzmann law, Stefan Boltzmann's constant. Now, important to look at this. Actually, we read Stefan Boltzmann's law with respect to Lambert's cosine law. What he says is that when you do absorption, what is actually is important is basically the cross section involved is what is important. You do absorption. Emission, always look at actually surface. The surface of, let's say, any emitting body, you are going to calculate the actual surface. Absorption, for example, that is the reason in conduction you neglect that surface, but you look at the actual cross section with respect to the length. So it is a cross section, because how conduction happens, you absorb from point A to point B to point C, you absorb. It is so called, it's the temperature get absorbed from one point to another point. Okay, so it is, this has to be really understood. You have a different wavelength depending on what body is there. Just now we have said, okay, we defined gray body, black body, gray body, etc. So these are quite similar, or rather quite known, and each and every body will come with its absorption rate. That means it's alpha. Then emission, that means how good you can emit. We can actually estimate that. Or rather, when you produce a particular body, rigid body, technically you should be able to tell me what is the specification, how good it can emit, how good it can absorb. So based on that, I can do my calculation. Right. Okay, this is important. Now, this is a range. Don't get me wrong. This is basically up to. It's not plus. I didn't say plus because there was, I think, one semester I did this. Minus 10 plus 25, then the student said it is 15. So to avoid confusion, so I've used now, instead of plus, I've used this divide symbol, but you won't write a divide symbol. So it's just that, imagine this is minus 10 up to 20 degrees plus. Okay, you read plus up to plus 90 degrees. Okay, it is not 9 plus 45, then you will have 9 plus 40, 49, then you will have no. It's just that to give you maximum, minimum. So just imagine this is a minimum temperature on your left, maximum temperature on your right. Okay, now all this you have covered. Batteries you have covered. You look at a battery, very tight. Battery is one of those tight operating device. Minus 10 to 25. It's very tight. Okay, very tight. Then you will have other. You see your battery units are all okay. But the good news is that we have our solar array, for example. Now solar array. Gallium arsenide is one of those photocells that you have, and this is silicon rays. Silicon rays basically has a bigger, it's smaller compared to actually gallium arsenide type of photocells. Okay, then you have your propulsion system, and you have telecommand, telemeasure, all the transponders. You have altitude orbit control system. So you have, if you look at gyros, for example, it is also reasonably quite tight. You can't actually go into a freezing, almost minus 10 or minus 20 degrees. Then you will have errors in terms of gyroscope. So these are the typical operation region that we have. And what we can learn from here, mind you, we have covered electrical system already. We will cover propulsion system. We will cover all these subsystems. At the end of this semester, you will have a good overview of all the subsystems available in the satellite. And here is just telling you, look, all these subsystems come in a different minimum and maximum temperature. You, thermal control system, better provide me the actual regime so that I can operate. That means I have to ensure that this happens. Now, just to give you a tip, if you do an average here, just to give you a tip, technically speaking, if you look at most of the satellites, if you sit inside the satellite, you will feel that the temperature is around 10 degrees plus. Most of the satellites. That complies to, if you maintain, just have a look at this. If you have 10 degrees, you can maintain 10 degrees inside. You should be able to operate all these subsystems. Okay? So it is not like you go from one compartment to another compartment, the temperature is 50 degrees. From one compartment to another compartment, you need to maintain, let's say, 30 degrees. No, that is not, that will be too complex to do. What you should do is that if we can maintain the temperature, the overall global temperature in the satellite around a mean about 10 degrees, all of them can survive. Operation can be successful. That's how you do it, right? But you can allow one variation. Yeah, even a plus minus 5 variation is fine, especially like battery units. You want to have a tight 10 degrees control of battery units, it's not easy. So you can allow that to happen. Okay, go on. Okay, this is very, very important to understand. Now, as I've said, it can be very complex. assume I'm flying. Okay, this is easy. Okay, this is planet Earth. I'm flying. Okay, and I'm in the sun phase, so I have sun. And when I am flying, I'm also, the satellite is also looking at the sun. Okay. Now, when I am actually not flying, that means not flying, but I'm in the eclipse phase, I'm not going to look at the sun. All right. Now, there is 3 major sources of heat load external to the satellite. 3. First, sun to spacecraft, to satellite, is going to heat you up. Okay? And what is more important to see is that look at which area it can heat up. That is the effective area. Keyword here, effective area of exposure. Then sun is heating planet Earth. Planet Earth, you have sea, you have soil, you have mountains. Just for example, let's take sea. If you look at the sea is like almost like a mirror. When you sun shines, it's going to actually reflect the ray. So the second one is basically what we call albedo. Albedo heat. Albedo heat, imagine it's simple. Planet Earth, like a mirror, receives the sun ray and reflects it. And that one is albedo. So the source of albedo is actually the sun reflected by planet Earth surface back to the satellite. 2 sources. Third one is Earth infrared. Now, Earth infrared is, name itself is called Earth infrared. So Earth infrared comes from the heat, the infrared heat that planet Earth has. So it is not mainly on sun shine, or it doesn't actually depend much on the sun lighting conditions. Which means if I go back, let's say I'm not looking at the sun, but I'm actually almost going into the eclipse, infrared can really happen. Infrared can still happen because it's not actually depending on the actual lighting condition of the planet sun. Just imagine when you have a sphere, when you heat up the sphere, when you heat up, there is a heat, and that heat, imagine this planet Earth, that heat is dependent from the sun lighting, and it can go into the eclipse. You can actually have that, you can feel the heat. It's just like that. So it always happens. Infrared radiation always happens normal to the surface of the planet Earth. Okay, important. Albedo, sun shines, then there is a angle, that reflection angle. But infrared always normal to the surface of planet Earth. That means normal. Okay. To be precise, if you have I think you will talk about pointings later on. It is, you can assume that this is technically speaking, it is like a zenith point. That means always is going up from center of planet Earth. It's actually going out. But don't forget, now sometimes when from center of planet Earth, when you go out, you will not get the actual right normal to the surface. So, but this ray is technically speaking normal to the Earth's surface. Every time it's just normal to the Earth's surface. 90 degrees normal to the surface. Okay, so it is almost like a, you can say, zenith pointing, or the rather from center of planet Earth straight up, but you will not actually get a 90 degrees in that, in the most of the time. So it is depending the position of the satellite. Okay, depending on the position of the satellite. So where exactly it is. So, but anyway, it is from the surface is 90 degrees. Now, if you look at this clouds, so you have a different, when your cloud, let's say albedo, let's say you have clouds, so the reflection is basically not much. Okay, then you have ground, you have water, So look at that. So these are the actual reflecting, I would say, parameter of albedo. So the average of albedo reflection is about 0.35. So 0.35 of what? 0.35 of the actual sun ray which hits the spacecraft. So 1371 watt per meter square from the sun hits here with the spacecraft, and you need to know how much of space is actually exposed to sun. Second, you take 1371 watt per meter square. About 0.35% of it, comes as a albedo back to here. And another one is basically an infrared. It's also given here. It's around 237 watt per meter square hitting our spacecraft. So there are three major sources. All of them are watt meter square, watt meter square, watt meter square. So you need to know where is going to hit your spacecraft. Sun is going to hit here. Infrared maybe will be hit at the bottom. So you need to know the effective place, effective area of that actual exposure towards the sources. Again, now that is the actual fundamental. So now here, this what you see here is all been averaged already, ready to be used. How this is been calculated or estimated is this huge formula. First component, solar heat flux, which is this, comes to here. Double integration, okay, solar angle, and this is a view factor. View factor of the sun, whether the spacecraft is seeing the sun or not. If you don't see the sun, then the view factor will be 0. Let's say you go to eclipse, this whole term will be 0. That's how it has been calculated, okay? And with respect to the actual effective area. Alright? So this is important. And remember, the function is at an angle. Angle of the actual view that you are looking at. Whether you are looking at the straight of the sun or you're looking at the angle. So this how it is being calculated. Albedo, same. Okay? Double integration. Again, the sun view factor will be there. So which means that when there is no sun, you will not have an albedo. Eclipse phase, you won't have albedo, you won't have a solar heat, but you will still have infrared during eclipse. Okay? So eclipse, same, but this is actually field of view of the planet Earth. Okay? It's a view factor of planet Earth. When you fly around planet Earth, you will always see planet Earth, so you will always have the infrared. But not necessarily you will always see the sun to have this both. So look at the quantity is important here. Solar heat, albedo, plus both, plus Earth infrared, plus dissipated heat inside your satellite from battery, etc., minus rejected heat, the one you can reject. This is where your thermal control comes in. This is where your thermal control is. And look at this formula. This is nothing but Stefan Boltzmann's law. Law of radiation. Looks like there is only radiation can help me here. And if I don't have this, increase and decrease the temperature with respect to my rigid body. Triple integration here. Okay? So if I don't have this, this is going to increase maximum. Okay? So in order for you to survive, just to tell you, this plus solar plus albedo plus Earth infrared plus dissipated heat supposed to be rejected by this thermal control system. Then you can survive. Alright. What you see here, what have I explained to you here, these figures came from an average of this operation. This equation, solar heat equation, albedo, infrared. If you want to do one by one, you can start actually doing this, but it's already been done and that average has been calculated here. That is the reason you don't have to go through here. straight we can say that, look, typically average about 1371 watt per meter square is what is going to affect your spacecraft from sun. And typically about 0.35 of this value is going to hit your sun. And typically about 237 watt per meter square is going to also hit you here from infrared. I mean, you don't have to actually calculate, it's already been estimated, but where this came from is through this particular formulation. And this is the angle, as I said, this is basically to facilitate. The angle is important, as I've said just now, angle is very, very important. Alright, go on. Okay, now this says that instrument power dissipation. We talked about instrument. So look at the power distribution that you have. This is a reflection of equipment, heat loads. Now, US lab and US hub basically is like a capsule. So look at that, heat load less than 500 watt, you have 88%. Less than 100 watt, you have 60. What he says is this: if you embark, please understand this, if you embark a very high power consuming equipment, be prepared for a lot of heat generated by the equipment. That's what he says. So if you are thinking to put a high power consuming equipment on board a satellite, make sure you are loading actually the heat thermal control system. Actually, you're loading it. That's what it says. Okay. So if you have a low power consumption, you have a lesser heat generation. So in a way, now when you want to actually procure a satellite, you want to actually go for low power consumption. Therefore, it is going to be a low power dissipation. So dissipation is low. So it is much, you will not burden your thermal control system. That's important. But if you put a human on board, you can't run away. It will be actually you'll fall in this category. You have a lot of equipment actually to maintain the human's comfort zone in space. Okay, this is interesting. Since we talk about the human, now let us see even our body. Okay, our body. If you look at it, sensible heat. There are two things. This is what is happening. You breathe, skin. There's a diffusion, sweat, etc. Even Malaysia is even more. In fact, it's hot. Then you have conduction. How conduction happens? For example, I'm touching here. Conduction takes place. I'm holding a pen. Conduction takes place. How convection can take place? Probably convection is this. You have a airflow here. So if you have a airflow, that can be actually through. You can actually take away the heat. That is how convection takes place also. Okay. So convection takes place. Radiation, automatically it is going to happen because I am a heat emitting body, so radiation should happen as well. So if you look at all this thing, latent heat accounts for what? 21%. That's about 10 to 50 watt per meter square. So if you look at the body, if you look at it, so that's about 21% actually goes to the latent heat loss. Latent heat loss is what? Latent heat loss is that the temperature would not change. That means the state might change. For example, boiling. If you boil water, boiling, this is a single temperature. There's only one temperature. Now, it doesn't change the temperature. If you keep on boiling the water, if you start measuring it, it will be still showing the same temperature. 100 degrees Celsius. That's it. It keeps on going 100 degrees. Oh, it might just have a small variation, but it will be actually almost there. Okay? So that temperature, even if you keep on boiling the water for next 1 year, the temperature will be still at the same level. But there is a change of state. The water becomes vapor without changing temperature that is latent. So our body, 21% is actually accounts for that. Sensible heat is going to change our temperature. Okay? Yes. if you hold something very cold, let's say you hold an ice cube, you will feel cold because there is a change in the temperature. That is a sensible heat. So human has this. So let us actually look at the sensible heat. So this one you don't have to worry. 20% it's not going to change our temperature, the body. We are worried about that sensible heat. Because sensible heat is going to change the temperature of your body. So now if you look at an astronaut, this is what actually is going to do. So if you look at the heaviest activity, he's going to actually lose about, if you look at the rate, about 250 for heavy activity. So for example, you do cycling to keep him fit on a space station, for example, that's what happens. So there is so many, and all this heat that you have, okay, heat loss, all this heat is going to go into the cabin, and you need to manage it. So let's say you have about four astronauts doing very heavy activity like cycling. You have about 1,000, almost 1,000 watt is emitted to your environment. So you have to manage. Who's going to manage? Thermal control system will manage. Okay. Likewise, this is just to give you an example. The same amount. That means if you are equipped with clothes, okay, is without clothing and the heavy clothing. What it tells you here, the actual temperature regime that I need to maintain outside. That's what it tells you. In fact, the actual condition of a space station, for example, it also depends on what kind of clothing that you are going to wear. So what tells you this is the requirement of the actual thermal control system that need to maintain about 20 degrees of temperature in the cabin. This is quite typical for human to survive, because obviously they are going to be at least about 0.5. They cannot be wearing a full suit every time. No, they will be somewhere in this region. So about 20 degrees is almost okay for them to live. Okay, this is what it says. So who's going to provide you this temperature regime in the cabin? So it's going to be very challenging because we have multiple heat spots, and in satellites we have multiple, or rather we have a constant heat spots. It's not moving, it's constant. Okay, but here we have multiple heat spots which moves around. That means it's very dynamic. It's very challenging for thermal control system, basically when you have a human mission. Go on. Okay, again I want to give a snapshot. So it means that for our purposes, this is important. Of course, external heat loads also, it varies. The further that you go from planet Earth, this equation changes, because sun will be predominant there, but Earth infrared will be weaker. Albedo also will be weaker when you move far away. So the example that I've given you here, you can consider this very relevant to low Earth orbit satellites or spacecraft. Okay, this is very common because we have a lot of actually low Earth orbit missions, Earth observation missions, etc. The one that you are doing at the moment, the project that you're doing at the moment is also will be actually, or rather all the exercises that you're doing also will be actually referring to low Earth orbit satellites. So again, a nutshell gives you this. 3 sources are available. Sun, straight to actually, can be any rigid body, can be space station, can be satellite, can be small satellite. What matters is that tell me how big is the exposure. I can quickly count or calculate with respect to watt per meter square. Then my second source would be albedo. Albedo is average albedo, as I've said just now, it's about 0.35. 0.35 times by my M sun, which is 1371. That should give me the actual albedo. More importantly, you must know how much of the actual space, or rather the surface, is exposed to this albedo. The final one is basically the Earth infrared. So Earth infrared, technically all this below areas normal to the orbit will be actually exposed. You can calculate. So this is the typical one you have. We have already discussed this as well. Go on. Okay, this is interesting to understand the actual parameters. Albedo versus inclination. Now, this data is from NASA basically. They update this. You can search and you can have that. Keras data. You have that. Now, let's look at this trend here. Now, this is basically the albedo's percentage. Albedo's percentage. As I said, we have accounted for about 30, we say 30, 0.35. This is where we are. It's about average of this, okay? Now, and we look at it, and for a orbit inclination, for orbit inclination, let's say about low Earth orbit, let's say about 80 plus. That's where you hit around here. For 80 sun synchronous, for example, 87, for example, 80 to 90, then 87 in fact. Then you should be able to actually get a 0.35. Now, please do watch here. Now, at inclination about 20 over, it shows me a very low rate, actually. Very low. Why this happens is because, now, if you look at the sun, as we have learned that it is in an elliptic plane. Sun actually sits on the elliptic plane, that is the plane of which belongs to the sun. And on this plane we have all the other planets, and planet Earth is also there. And if you look at planet Earth, it's tilted about 23.4 degrees. In fact, with respect to the elliptic plane. So elliptic plane, our planet Earth is tilted about 23.4. Okay. So what exactly means when the sun shines, and let's say our satellite is there. When the sun shines exactly on the elliptic plane, it goes and hits the planet Earth, right? Now, I know for the fact, when you want to calculate the orbit, you have to calculate the orbit. You will learn in space mechanics. You will actually estimate the orbit. You will try to design an orbit with respect to the equatorial plane. So what I'm saying is that the equatorial plane of planet Earth is tilted about 23.4 degrees with respect to the elliptic plane. So elliptic plane belongs to the sun. Equatorial plane belongs to planet Earth. Okay. Now, if I have an orbit, satellite orbit is based on the equatorial plane. So when I have that, elliptic plane, and then our equatorial plane. So when I have a 23 degrees of inclination, which means that I will be up about 23 degrees, almost to the elliptic plane. That's the orbit. So at that particular orbit, sun is basically shining at the back, right? At the back of me, the sun, spacecraft, and planet Earth. Now, in order for me to have albedo means what? Mirror reflecting me. Now, let's say there's a torchlight at the back of me, shining, and there's a mirror in front. The mirror can't see the light because I am basically a sort of a barrier. You won't see the light. But when the sun moves here, obviously you can see. So that is the reason at a 23 degrees, technically you will have almost like a shadow effect, and it becomes and the mirror can't actually just reflect because the rays are actually not going and hitting it literally. But when the sun moves, let's say my orbit inclination moves, that means I'm in a higher or lower orbit. Let's say in a higher orbit. When I'm in a higher orbit, let's say sun is shining there. When I'm in a higher orbit, I'm here. I should be able to actually receive the reflection of the sun, because albedo, the planet Earth, acts like a mirror and reflects the sun. Okay, that's why you see that it's quite minimum, and it gets better when you have the albedo angle. Reflection angle gets more and more and more, better. When the inclination actually goes higher, basically it goes, the reflection happens, and you can actually get a better albedo hitting your body. And now don't forget, you want more or you want less albedo. We always want less albedo. We want less actually heat. Yeah, less heat. So we want less albedo. But the thing is that we cannot say we want less amount of sun exposure. We want a lot of sun exposure so that we can have we can generate the power in that sense. Right? Go on. Okay. If you look at Earth infrared versus inclination, now this is different. Now, if you look at it at 23.3 degrees, 23.4 degrees, it looks like we have a maximum Earth infrared, I would say, effect. It is true. Why is that? Same condition. I'm here, elliptic plane, sun is at the back, satellite, and that is actually planet Earth. I told you, I am basically right. When I'm in the elliptic plane, I am a right spot facing the actual planet Earth. So at that time, at that spot, I have a maximum normal infrared receiving opportunity, I would say, or rather angle. So it's exactly very normal to the actual emission. So you get a very high peak. But when you start actually in a very higher altitude, higher inclination, there is a tilt angle already. So when there is a tilt angle, then it will be calibrated, it will be lesser in fact. It will be lesser. The heat will be actually lesser because you have a higher angle. It's as opposed to, remember, albedo, when you have a higher inclination angle, the reflection is better. Okay, you reflect. But in this case, it is not a reflection, it's basically coming from a source. The source gives you, if you want a good visibility, or rather if you want a good angle, or you want a good heat generation, you should be actually looking straight normal to the actual source. So when you have an angle, you have the cos angle will actually will make sure your actual amount will be reduced. So just like that, the sun, when the go back to the before this here. Okay. What I'm saying that if this is actually it's a normal to the surface, 90 degrees, you will have a maximum heat generated. In here, Earth, planet Earth, it's the same thing. You have a heat. And normal, you will have a maximum basically heating. Right? Okay? Alright, so this is albedo versus infraflux. As you can see, this is the actual maximum infrared flux that you can have. Okay, 200 watt, around about 200 watt. Okay, with respect to the actual altitude. Now, as I mentioned just now, if you go higher altitudes, technically you will have a lesser effect of this because Earth infrared gets weaker when you go further. Albedo gets weaker when you go further. So it is very predominant for low Earth orbit. Very predominant. It's going to heat you up. But when you go further, you will lose these two, but then your heating of planet Earth, sun towards the spacecraft is going to get high, or rather it's going to get predominantly big. Okay? Because exposure, you're getting near to the sun. Okay, go on. Okay, this is another aerodynamic heating versus altitude. When you are at a very low Earth orbit, there's a friction, aerodynamic friction. That means there's an air. When you fly above the air, let's say planet Earth, satellite is flying, atmospheric layer, you're going to fly, and there is a friction. And look at the amount of friction, look at the amount of energy that you have. The heat flux is about, look at that, at 100. Now, if you will see in rocket technology, our re-entry start about 120 kilometers of altitude. That's where the re-entry trajectory starts. You look at the heat, it's almost folds, multiple folds would have. Okay, and you can't, if you can't handle it, you will just disintegrate. That means you will just burn. so much of heat, and we will see in rocket technology how basically we can mitigate that. What kind of thermal control actually we can have, and how to actually avoid this much of heat when you want to re-enter. Satellites are not designed at the moment to re-enter safely. When you re-enter, satellite itself will actually disintegrate and burn because it cannot survive. But launch vehicles, especially the return capsules, let's say SpaceX, for example, Dragon, that would be designed basically to re-enter safely, to handle this much of heat. Okay, got it. Okay, this tells you. Now the temperature can be very, very tricky when you want to actually start calculating. You calculate based on the view factor. These are the view factor, F, big F and small f. Big F is actually related to the sunlight itself. That means whether you're looking at the sunlight itself and what is the actual factor. Is it maximum view, minimum view? And this is, F is actually the satellite itself. How the satellite is actually looking at the sun. So sun is actually looking at you, satellite is actually looking at the sun. So because not all the parts in the satellite will look at the sun in the same manner. You will not. Different parts will have a different view towards the sun. Sun may have only one view because why? Sun is so huge and satellite is so small. But the view factor for the satellite of different components in the satellite, especially outside the satellite, will have a different view factor with respect to the sun. So it can be very, very complicated when you do this. When you start actually looking at the temperature built up here, and you want to start calculating, it becomes very, very complicated. When you can't actually do it, well, I would say parametric analysis, you can't actually just do it just like that. It has to be in a numerical approach. Analytically, it becomes very complex because you need to know all these view angles. Let's say you have a solar panel, you have the body of a satellite, you must know how the solar panel is looking at the sun and how the body is looking at the sun. Solar panel left and right will look at the sun differently, you know. But the sun, for the sun to look at the satellite, it is the same because it's a very small, almost a small spot. So it might be only very, very one view factor. But you can have a multiple view factor from the satellite, depending on that. So that becomes very complex. So that is the reason to simplify the problem, we still use this approximation for analytical calculation. We have just like what I said to you. Go on again before this. Before this first one. Yeah, that one. Yeah. So instead of going through this formulation can be done through numerical approach, but analytical approach we can use this formulation because all this being averaged already. You have an average albedo affecting, you have average sun, you have average infrared. We will use this. Yeah, but there would be a very slight variation, but this is in fact for a maybe low cost mission, etc. This is how we can do it. Yeah, right. Okay. Task of thermal. Before this, we have covered what is the goal basically. Now we need to actually ensure that temperature limits that you have. Now once you know how much heat that you have, the rigid body, you should be able to actually calculate the temperature by using basically the MC theta. It's easy, depending on the actual contact area. Then we will do an exercise with that. So analysis of external and internal heat flux. Analysis of external, we have already done that now. Internal, let's see, maybe battery, how much battery actually is going to generate and all that. That is the heat that we have internally. Both actually we should be able to calculate. And then design modification or verification, optimization, etc. Based on these two, we can actually now look into what kind of options that we have in order for us to cool down the actual thermal heat from the spacecraft. Remember, I can only use radiation to to eject any heat generated in my spacecraft. That's the only way. So I have to think now what are the options that I have. Analysis method, thermal modeling, geometric math model, thermal math model. Geometric mathematical model is very complex. Reason can be done numerically because each and every component of the satellite you need to actually have generate its geometry and then see how this geometry is actually looking at the sun and then start calculating or estimating the actual temperature generated with that particular component. Thermal math model, slightly simplified. We can use spring method basically. We can use that spring laws, parallel series spring laws, just like you have done in your electrical maybe courses. That actually we can use that. And for analytical solution, this thermal math model which can be applied. Then you have analysis software where you can use a finite element basically to do this approximation. It's quite common. Thermal test, as I said, if you have already that devices designed, then we can actually look into the thermal test that you want. Okay, now again, as I've said, repetition. This is just a radiation, conduction, convection, and heat flow. This is done. So if you are looking at a finite element model, the actual temperature for each and every nodes, because when you do finite element modeling, you will be exposed maybe to do maybe stress analysis, etc. So you can see we can use that technique basically to also to approximate the temperature difference. So this is quite very general. Current temperature, the delta temperature. So this is how the approximation is done. Now again, the conductance here, this actually incorporates. It's also valid. You don't have to be afraid if you. It's also valid for a different material, for a different distance, as we can actually keep on producing up to, let's say, how many materials you have there in place. All right, gone. Okay, this is what I've said. Now it's easy. Look at that here. So if I treat this as a spring, so this basically is a series spring. So technically I can use the same law that we have used in electric in order to calculate this heat transfer. So you can have layers after layers after layers after, depending on the lambda 1 up to lambda k and diameter. So accordingly I should be able to estimate the k conductance. Once the k is done, I lump the k from, use the k, and then based on that temperature, start temperature, or rather point A to point B temperature, that can be actually calculated. Normally one should be measured or known, and another temperature should be actually calculated. That's how it is, right? Okay, go on. Okay, I think we will continue with the hardware maybe in the next lecture.